Okay, I think I got disconnected. Sorry, guys. Let me share my screen back. Okay, so today we will last session we have covered a bit of analytics. Okay, and then we actually gone through some correlation analysis, right? Like today we will see something more. Okay, like comparing multiple values together. Okay, so in this correlation analysis we can figure out like the relations between multiple different parameters, hyperparameter features, basically I would say. And these features helps us to understand in more detail like which of the columns are kind of correlated. But by the way, all these features are contributing into our data sets, so that there is no doubt about it. But yes, most of them are basically working in respect to these data sets. Okay, and it is completely tuned, okay, altogether. Now today we'll see how can we kind of compare multiple values. Like so far we were only comparing one single feature or one single column. Okay, in terms of understanding the overall data set. Okay, today and now we will see and map multiple other values and columns, and we'll compare between multiple data sets. Okay, ideally this is a part of an EDA. I'm just keeping it short because EDA process is very long. In real-time industry, EDA process takes near about, as per my project, I've been working from past 5 months in EDA. Okay, little bit complicated data sets, which where I am working into healthcare. Understanding the healthcare by itself is a bit challenging. Like a lot of domain expertise are required, and then try to figure out like what are the root causes of a particular disease. So this takes a bit time, right? So basically, typical EDA takes a bit time, like figuring out which all the columns are important. In fact, which other features are important for some particular predictive models. Okay, so from a data engineering perspective, we don't need to build any predictive modeling, or we don't need to do all of those. But majorly, what is more important is like getting into details of how and what data scientist needs. Okay, because the data engineers are the one who basically design the first level or create a chunk of first level data, and then it passes to data science team or analytics team to perform the analysis on top of this data. So the reason of this EDA, as I mentioned yesterday and iterating again back, okay, not every time we do the EDA. In fact, okay, there are some projects where we feel that EDA has to be done, and that's what we don't do on a daily basis. But major instance of this EDA is most likely that we do it when the data sets are, we need to create our schemas. Okay, like L0 schema is there, L1 schema, L2 schema. Okay, and in fact, in terms of database, okay, there is a concept called normalizing database. Okay. So what is normalizing database? So it is more like you are not only dependent on some subjective data. Okay. So you are basically going and kind of, there are typically different type of normalization. Like you are increasing the relationship between the data. Okay, that you don't kind of reiterate the same data again and again. Okay, all the uniqueness in the given data should be present in a single table. Okay, all the relations between the tables should have it kind of there in one single place. Okay, so that you don't need to create multiple tables for each and every explanation. Okay, so that's what is your normalization. Now, what you have to do is, in terms of very large data sets before we apply. So normalization in a layman terms, if you want to understand, it is like there should not be any same duplicate record for any other feature. So any data which is getting into a categorical sense, you create a category and put it into in terms of columns. Okay. So there are different levels of normalization, okay, that we will learn in our SQL series, okay, in more detail. I'm just kind of throwing towards like how this entire normalization works and why we do this EDA to kind of best fit our normalization. So in general database, we do normalization up to multiple levels, 1, 2, 3, 3 levels of normalization. But majorly what is most important is, apart from this normalization, it is like the data set that we have it, L0, L1, L2, should be usable for your data science team, right? It should have certainly, it should be related to your data science goals or the predictive goals. Let's say you want to predict the price trending, okay, in the market, or you want to predict the trend of a particular commodity, okay, in terms of retail space. Or in this case, the use case which we are solving, it is attrition, right? We want to predict the attrition rate, okay, whether a person is willing to continue in an organization or leaving the organization. So that's what we are trying to predict here, okay? That's what we say in this entire data. If you see this first part, okay, figuring out what is our target. Attrition is our target. So this is our target. Target means this is what the data science team needs to predict. The data science team will take this and predict, okay, that whether given these are your features, a person can iterate yes or no. Okay, so that you can make a predictive model, and whenever the values are matching with iteration, like probably that the person will iterate, okay, you can stop that. You can figure out that which features or which particular column is making that disturbance or not. It's kind of giving more trending towards iteration, right? So you can figure out all of those, and you can basically save some part of your targets and basically focus on the business aspect. So that's what the objective of end-to-end project, starting from data engineering until resolution of the business, like including data science. But as I mentioned, like in normal database normalization, okay, what we do is we basically do L0, L1, L2, L3, L4 normalization. That is all fine, but there is an aspect to it. This normalization should be adhered to data science objectives. So whenever you are taking an L0 table, which is your raw data, you are normalizing some of the columns, means you are making it more generalized. Okay, normalizing means the row or the records or the data should not be redundant. Okay, should not be, means any point of view, there should not be any sort of anomalies. Any particular record that we want to pull in or pull out or whatever we want to do, it can be easily doable with your SQL query from that same particular table, right? So these are some basic estimation or assumptions, you can say, while we normalize a table. Now that normalization has to be happened based upon the data science requirement, okay? So that those columns which are important, in fact, okay, should be taken. The rest of the column you can drop it. Maybe you should you just a minute. So rest of the column you can basically drop it. So this is what is part of your EDA, okay, and that's what we are going to do eventually today also. We will spend some time with this EDA. We will continue to do a basic EDA. These are the basics, basic EDA. Okay, there are a lot more things that we do and kind of compile. Again, then we will be moving to a data science program. So we will get diverted. So until we will just see how can we get a deeper understanding on all of these records, and then probably we'll move to our SQL database. And there are a lot more other databases that we will be seeing it, and in general. Yeah. Cool. So let us move towards. We'll be continuing with this notebook. In fact, okay. Probably all the variables are not lost. I hope so, because the notebook is continuously running from yesterday. Yes, variables are not lost. So my variables are there. I was working on a different notebook altogether. Yeah. So let's continue from here. Now, given that, let's see the correlation once again to continue to maintain the continuity. Okay. So let's see these correlation. You can see it's negatively correlated, and on top of it, it is basically positively correlated, right? So negative correlation to positive correlation. Now, what does it mean? Negative correlation means that if X and Y, two variables are there, if X is increasing, Y is also increasing. So this is basically positive correlation. If X is increasing, Y is decreasing. So this is basically negative correlation. Okay, so this is what we are trying to learn, okay, from this entire data sets, okay, where we are trying to see how it is correlated, because that will tell us that if I take a particular value, okay, whether that value has some relation with the other value. So for example, let's take, let me clear, and let's take one example here. So if you see job level 0.51, okay, 0.51 at age. So it is 0.51, no negativeness. It is more into positive correlation. And what does it mean? Job level is increasing with increasing age. Okay, so job level is increasing with increased age. Next, monthly income 0.50 is also increasing with increasing in age. So monthly income is increasing with increasing age. Okay, let's see some negative correlation. Okay, where there is a red color, it will be a negative correlation. Let me erase this too. I don't see any red color, in fact. So it means that all these data are positively skewed, means positively correlated with most of the data sets. I don't see any red color or orange color data. There are some negative values which are minimalistic, right? Okay, number of companies worked. Okay, so these are in negative values, but they are very minimalistic. Yeah. So now moving to, let's say this 0.95, you see monthly income 0.95, which is strongly indicating with job level. Okay. See monthly income 0.95, strongly kind of it's a strong indicator altogether for job levels. Okay. Now what we do over here, monthly indicator with job level. So we can see that this particular indicator is quite natural. Like if the job level increases, okay, monthly income also increases. It's quite true, right? So income will increase. Somebody who is just staff or doing a clerical job will not have a higher income comparative to somebody who is kind of a director or any given such position with a higher job role. So we can see that that is kind of having a more salary. Okay, they would be bagging a more salary, right? Then cool. There is no negative values much. There are some, but those are kind of, you can treat it as a negligible. It's coming within the no coefficient. Like it's basically telling that there is no correlation. Okay, there is no correlation at all between the data sets. So this also predicts that. Now, this doesn't mean that it is not contributing to your outcome, which is your target. Okay, this doesn't mean that it is not contributing to target. Okay, it is contributing to target, but doesn't have intercorrelation. Okay, means for an example, if you see one particular example, this distance from home. Okay, they are all near to zeros. Distance from home all near to zeros. But in our yesterday's example, what we saw is like it is right skewed. The data is right skewed, right? It means that there is some impact, there is some relation with the target as well. People mostly love to have a lesser distance comparative to the larger distance, okay, from their workplace. So people love to have a lesser distance. One, they don't want to travel much or more as comparative to the other distance, other places, right? They want to visit their workplace daily, so they won't be traveling much. So it is rightly skewed. So this doesn't mean that it has no correlation with the target. It has correlation with target. Okay, people who are leaving the job, we will see in future. Okay, we'll try to figure out people, those who are leaving job, those who are participating in attrition, like those who are leaving the organization, distance from their location can be a higher, can be, okay. It is one of the factor, not necessarily, but it could be one of the factor, right? So you cannot drop any of the columns which are not correlated, kind of. But here correlation means that it is interrelation between the features, but all these features have certain relation with the targets, so you cannot drop any of them, right? At any point in time, these targets, these features can change their relationship. Cool. So from here we can understand there are few features which are highly positive, okay, like this part, okay, years at company, okay, then years in current role, okay. These are some of the part where we can see that there is a high values, okay, present over here. Means high positive coefficients are present, so it is positively correlated among these features. Good. So next is, let me now do an analysis on like what we found is from this correlation, monthly income is one of the interesting factor with the job level. Monthly income is also an interesting factor with total working years, okay, and in fact with all of these other parameters, percentage salary hike, okay. So all of these parameters are, you can see performance, percentage salary hike, okay. This has also some relation, okay. So let's take this and figure out. So let me see what was the variable HR data, right? So columns, sorry. HR data. So you can take daily rate. Okay, we can take this daily rate. Let me take it from where we need to write it down. So daily rate. And then hourly rate. Hourly rate. Okay. Then we can take the monthly income, right? monthly income. Then percent salary hike. Okay. So daily rate, monthly income. Okay. Daily rate, hourly rate, monthly income. Okay, there is another parameter called monthly rate. So let's include that as well. Okay, daily rate, hourly rate, monthly income, percent salary hike, dot columns. Okay, dot to list. So this is our columns. Okay, so we converted, we took all these columns to list. Okay, so now we are going to plot these columns into in a box plot. Okay, box plot helps us to understand what is the mean, what is the interquartile range. Interquartile range means you can imagine as a majority of them, like 25 to 75%. Then it also helps you to understand whether there is any outlier present or not, means something that is quite high or different from the mean. So all those factor comes into the mix. So here what we'll do is plt dot figure. Let me include the fixed size. Fixed size is equal to 10 comma 10. Sorry, 10 comma 10. So for I in, okay, let me enumerate. So for I comma variable in enumerate columns, plt dot subplot. Okay, we are creating a subplot, means in a single 10 comma 10 figure, means in a single figure like this. Let me plan it out. This is your 10 comma 10. Okay, 10 comma 10, and I want to create small box plots in this 10 comma 10. Okay, and I want to create kind of 5 box plots. Okay, 5 for each of these values. Okay, 1 2 3 4 5. Okay, so let me do that. So plt dot subplot 3 comma 2 and comma I plus 1. SNS dot box plot HR data attribution. Sorry, attribution, right? Sorry. Let me take the HR data attribution. Okay, comma HR data. Okay, I will pass the variable here. I will explain, guys. Don't worry. Let me just write this. Palette is equal to, let's say, winter plt dot type layout plt dot title. Sorry. variable plt.show. I'm getting some warnings. Okay, these are basically the Seaborn version issues. So that's fine. Okay, so let me explain the code first. So what we did, plt.figure size fixed size means we are giving some figure boundation size like 10, 10. And then for I comma variable in enumerate columns. So these are our columns. Okay, one by one we are taking it up. And then we are plotting those columns. Okay, so like daily rate, then hourly rate, then monthly rate, okay, then monthly income, and we are plotting this column with respect to iteration. So daily rate, okay, so for I in variable, I comma variable, so it is like we are taking daily rate as well as iteration, okay, and then we are plotting it. Then we are taking hourly rate and iteration, and then we are plotting monthly rate, then iteration, then we are plotting monthly income, then iteration, then we are, so like that. Okay, so daily rate is with respect to iteration. Yes, no. These are the box plot. Now from this box plot, what we can see that there is some change between these two box plot. The yes one, okay, the people who left, okay, there is slight change in the mean. Okay, so probably their daily rate was quite less. The mean, the interquartile range also a bit lower. Okay, but that's not a very significant difference. But still, it is lower. So daily rate is less. If you come to hourly rate has no significant change. I can see both of these interquartile range are at same levels. So there is no much significant change, and there is no much change in their maximums and minimums. Okay. Coming to monthly rate, it is also almost bit higher. In fact, the monthly rates are a bit higher for those who left rather than those who didn't left are within some branch. But this high is something negligible, which you can ignore it, because it's something just a quite small percentage of people are basically bagging more monthly rates comparative to the people, those who are not at no. Okay. Next is this particular, yeah, this makes a lot of story here. So monthly income. So monthly income for those who left the organization is quite less comparative to the monthly income for those who are in the organization. And if you see that there are some outlier folks, okay, who are earning a lot, but they also left, who are into the outlier zone, okay, this particular region, right? And if you see this part from till here, this is also the total IQR is quite lower. And in fact, if you see it's near to the mean, means the 75% range, 75 to 100% range is just near to its mean value, okay, or somehow greater than the mean, but not much. And this could be one of the reasons that their monthly income is quite less, okay, and that's why they have probably left the organization. Okay. Next is at the bottom, you can see that there is a percent salary hike, and I don't see much change. The mean are always at the same. I can see that the percentage, the IQR is not exceeding 16, where so it's not exceeding the no IQR. So it's somehow lesser. Okay, the major IQR is lesser, which is between somewhere around 13 to 17%. Okay, not touching 18. So 13 to 17, whereas the people who didn't left the organization is also between 13 to 18. So not much significant difference, but the major significant difference out of all of these graphs came in monthly income. So monthly income and iteration, okay, they are much more related. Okay. Like they are in iteration, monthly income is more contributing comparative to any other parameters. Okay. Cool. Any questions? Anyone? Anybody? Okay. Moving to next, let's take some more other parameters and then see. Go back to the correlation and finding that these parts are very interesting. So years at company, years at current role, and years since last promotion and years with current manager. Okay. So let's take this part and then do the analysis, okay, with respect to accuracy. Okay. So similarly, we'll take columns is equal to HR data, and we can pass on those values. That depends on the algorithm that you want to choose. Okay. If you are going for kind of regression and all, then probably we'll be removing it. But if I'm going with decision tree and all, okay, based upon what we are doing. This is mostly a classification problem. Probably we're not going to remove the correlated features. But if I would have loved to go with regression based model, then would have to remove those correlated features. Let me write one by one. That depends on the algorithm that you choose. That's a good question. But I am not going to, as a data engineer, I'm not going to kind of apply the algorithms anyway. So not necessary for us. Until just to see even these EDAs also at a very deep level is not necessary. But it is very useful in terms of answering most of your business questions. Like, it's not only the data engineer creates a database and then their job ends, but they mostly do the mining part. At that point in time, you might need this to kind of get accustomed to it. So yeah, that's the reason. So years at company, right? Company. Years at company, years in current role, years since last promotion, all are camel casing, years with current manager. Okay, let me write all of these. Years in current role, years since last promotion, years with current manager, and yeah, I think that these 4 years with current manager, years since last promotion, year in current role, years at company, training time. Training times last year. Let's take this. Training times last year. Okay. Then dot columns dot to list. That's it. Next is plt dot figure figure size is equal to, you can pass the figure size 10, 10. So as we have done above as well, for I, where in enumerate, and then you pass on the columns. PLT dot subplot 3, 2, I plus 1. Then SNS dot, we are going to create a box plot. So SNS dot box plot HR data. Attrition. HR data attrition, HR data where palette spring PLT dot type layout, PLT dot title, PLT dot show. Okay. So here what we can see that for years at company, people have spent less amount of time for those who have left the organization. So those who have left the organization, they are basically taking less amount of time in experiencing the organization. Probably this could be one of the reasons that they are not experiencing the company at a high space, means with enough time. And there are some outliers as well, which we are not considering it. But majority of them are living between somewhere around 3 to 6 years, 3 to 6 years on max. Then years in current role, what we can found is most of them with current execution, means years in current role, most of them are in current role. They have a very least role change. So which is between 0 to somewhere around 4. So 0 to 4 years. They have a least role change. And this is the limit. Okay. And these are the, you can say, these are the outliers, right? So what we can find out that 0 to 4, okay, this is the time, like most of the people with similar job role, current role, they are leaving, majority of them. So it is also very important that an employee should have an incremental role change, right, with a due time they are spending with. Then years since last promotion. So 0 to 2 years, I can see. So 0 to 2 years, majority of them were promoted, but they left, and they left within 2 years, like we can see here. Whereas if you see the IQR for no, means people who didn't left have a greater IQR, interquartile range. But here the interquartile range, even though years with current manager, probably this is also one of the important fact that there is no change in management, there is no change in increment. So years with current manager and years in current role is, I can feel that there is some sort of match we are getting. Okay, years in current role and years with current manager. Next is training time last year. So there is no impact with training time. Okay, there is no much impact with the training time. So these are some of the analysis that what we found. Those employees who spent less time at company in current role or with manager have a higher chance of attitude. So you can write down those observations like mark down those employee who left or who spent in fact less time at a company or in a current role or with a manager have higher chances of reaching. Okay, and the final observation was training is not an important aspect of accuracy. Training is not an important aspect of accuracy. So these are the observations. Basically, observation. And it is one of the best practice to kind of write down the observation. Similarly, over here also, what is our observation so that you can refer it back. Employee with daily rate and less monthly income, okay, are more likely to adulate. Daily rate is less and less monthly income. They both like to adulate. So let us write observation. Employee with daily lower daily rate, I should write it as lower daily rate and less monthly income are more likely then what else? Monthly rate and hourly rate has no impact, so you can note it down. Monthly rate and hourly rate has no impact. And percentage salary hike, we can see that lesser IQR is smaller, so you can claim that less salary hike would also lead. So these are our observations that we have it with respect to this particular graph. Okay. So like this, we can do it for any given other parameters. Okay. So there are a lot of parameters. We can kind of create multiple such graphs for other parameters. So I will just limit up to this, but later on you can practice with other parameters as well, which you can explore while going through this notebook, okay, at a broader level. Now these are all numerical values, right? So numerical values are easy to compare in real time. We don't face much issues with numerical values, but major problem comes in when we try to deal with categorical values. Now, in terms of categorical values, one of the important technique is counting that occurrence. Okay, so that is basically your categorical value, counting the occurrence, counting how many times that particular part will come into an occurrence. So let's do that. So we have a couple of categorical columns. like yesterday we were noticed, these are our categorical columns, right? Affiliation, business, travel, department, education field, gender, job role, marital status, over 18 over. So these are our categorical listing. Great. So let me copy this, pull it down so that I don't need to scroll every time and can have an easy access to with this information. So first of all, let us create a plot view. Okay. So this time I am going to create a plot view based upon counting. Okay. So if categorical value, I want to put it into a stacked bar. So what is stacked bar? I will show you. So before that, let me pass on the data. So these are our arguments to the functions. Okay. Then we need to pass that what we want to kind of count. For an example, we want gender, like gender is one of the categorical features, and we will take attrition. Okay, gender and attrition. We want to get into a detail of that how many genders are there, like how many males are likely to attribute or how many females are likely to attribute. What is the percentage and all of those. So you want to get into the details of gender and attrition. Okay. So data and comma. We need to put predictor, comma target. So target is basically the categorical value, which is attrition. Predictor can be any such value like gender, or you can take any categorical value. Okay. Next is we need to count. So count is equal to the data frame that we want to pass. Predictor, we want to take that predictor, then dot n unique. N unique means all the unique values of predictor. Means for gender there are 3 unique values: male, female, and others. Let's say, just an assumption. Okay, so there should be 3 categories. Okay, so that is what is n unique. For a given predictor gender, there is male, female, and others. So that is what is here n unique, comma. Next, sorter. We need to create a sorter to sort the values. Means whichever value is having the highest proposition. So you want to take that. So data bracket target dot value counts dot index -1. -1 represents that you take the last value out, okay, and you take all the first top values and in a reversed manner, okay, so that you get the highest. Like if you see the value counts, yeah, these are our value counts. So it is always the first value is already sorted. And if you see the last one, this we don't need it. We only need these 2 things. We only need these 3 things. This part is something that we want to remove. So that's what is your -1. Okay. And already it is in a reversed form. Value counts already is in a reversed form. So you don't need to put anything else. Okay. So it is already in a reverse form. So dot index -1 will remove the last part. So once we do that, and then we need to create a kind of a pivot So in Pandas, like in your Excel sheet, you create a pivot, right, where you can get to see all the values present over there. So over here also we will try to create a pivot. So this is the table is equal to pd dot cross tab. Cross tab is a function of Pandas where you take the data and you take the predictor, comma, data of target, comma, margins is equal to true, dot sort values. You will be able to understand once I print this result. So I want to sort values by is equal to sorted. Okay. Already the value counts have a value sorted. Comma ascending is equal to false, means we are following descending order. Okay. Ascending equal to true means we are following ascending order. When we are putting ascending equal to false means we are putting in form of descending order. That's it. So this is the table one. So print table. Okay. Print table. We want to print a line of the star into 120. And then again we will use another cross tab where we will pass the same values. Okay. First cross tab is going to pass only one particular class. Okay. Like based upon the count value, we are just passing the target. Margins is equal to true. Just a minute, guys. Okay. Margin is equal to true, and we are just sorting the values. And then we are going to plot the actual cross tab. Okay. So it is like we want to plot the data. This is the information part. And then after this star line, so it is something like this. First we are describing, this is a description of what we are plotting. And then we are drawing a star line with this. And then we are plotting the actual graph. So for plotting the actual graph, we need to write few lines of code. So tab plot, so pd dot cross tab. First, let us write so data back with predictor, comma, data with target, next is normalize. Normalize is equal to true. So what is normalize? Means all the data. See what happens when you are taking a categorical value. A categorical count can be in thousands. Okay. Can be in thousands, can be in hundreds, can be in tens, can be in some numeric value, let's say 1 to 5. Any scale it can be, right? So we are doing this normalize to bring down the scale from 0 to 1. Means the count will be there is no issue. Only we are converting all those values between 0 to 1. Why? So that our categorical count can be easily measured in terms of percentage. Okay. So 0.8 means 80%, 0.9 means 90%, 1 means 100%. So that is what we are going to kind of experience it with normalized. This has some mathematical formula, so I will explain that bit later. Okay, let me write the code and then I will explain you the mathematical derivation. Sort values by sorter, comma, same thing, ascending is equal to false. Okay, now we need to plot it. So tab dot plot, kind of plotting is bar plot. Stack is equal to true. It should be a stacked bar plot. Then figure size is equal to the number of parameters we are taking, right? So let's say we are taking only one predictor, or if I take a 2 predictor, 3 predictor. So based upon that count of predictor, based upon the count, count already we are counting. So based upon the count, we will add one extra value, comma 5. So this is the figure size. Okay. So with less value, size will shrink. If with greater value, the size will increase. Okay. So PLT dot, we need to plot legend. So I will show you. Legend means basically some of the indicators or the colors that we are using should be mentioned, right? So location, LOC means location of the legend. So I can put it on kind of lower left. Location is lower left, and frame on is equal to false, means it's not necessary that you need to put that legend within the frame. So that's why. And put commas here. PLT dot legend location is equal to upper left, bounding box to anchor is equal to 1, 1. Bounding box to anchor 1, 1. PLT dot show. So this is your entire plotting. Okay, we have created a function and we don't need it back again. We'll be using this for multiple categorical, almost we can see for all the categorical results. So let us execute this. Now stacked bar, this is our function. So let me plot this. Stacked bar HR data. Let's take the first one. This attribution is our target. So we'll start from business, travel, department, education, gender, job role, marital status. So let's take business travel. And comma attribution. Yeah. Now what you can see here, the first part, if you see the explanation of the code, first we are counting the number of unique values based upon which we are creating this as well. Means number of unique values: travel rarely, travel frequently, non-travel. Next is we are sorting. We are sorting the values. You can see the last value is not there. Okay. Sorting means value count already gives in a sorted form. So it is all sorted by default. Next, this is the cross tab part, like where we are pivoting yes, no, and all. Okay. So we are pivoting our target, all the values, predictor values with respect to target. So this is what is our cross tab. Okay. And then another cross tab we are passing, and we are taking that cross tab value into plotting these values. Okay. So travel rarely. You can see 0 to 1, which is already normalized. So 60%, 60% of them didn't rejected no. So this is our legend. Okay. So this is our legend no, which says yes means people who have left. So near about 40% people left the organization for 60%. I can see some stat tissue. Just a minute. Probably somewhere I've used. Bounding box. Yeah, seems good. Cool. Okay. Yeah. So it is normalized, but I want to normalize in index. See, our index is showing 0 to 70% because 70% is the highest. Okay. As per this particular value. So I need to normalize through index. So that's what I was not getting, why this stack is not reflecting at this level. Cool. Let me rerun it back for our easy. Yeah. Now it is making sense. So you can see that 70% till 100%. So 30% travel frequently left the organization. So 30% folks who are traveling frequently left the organization. Travel, it shows a clear impact. From here, it shows a clear impact that people who are traveling are leaving the organization. Right? You can see travel rarely, the division means the amount of information is reducing. Non-travel, it's very minimal, so 10%. But if you see travel frequently is having a lot of more folks present in the bunch. Next, we will be kind of passing some more other parameters here. Okay. So this is with business travel. Now let me go departments. Now let us see with department is all the department, like people is frustrated or somebody may not like the department where they are working for, okay, something like that. So those things needs to be addressed here. So we'll be checking through whether there is any issues related to the departments or not. So let us do that. So coming bottom part. Stacked bar, stacked bar, and we need to pass HR underscore data, comma, the department, comma, at region, department, comma, at region. So this is stacked bar. So you can see that mostly people from sales are leaving the job. So people from sales leaving the organization. So this is quite an interesting fact. Okay. So this is something that we need to look around. Okay. And then human resource guys are also leaving. People who are hiring, they are also leaving. Research and development has little bit lesser, so somewhere around 85, but both of these are near to 80s. Sales, human, slight changes there, which is not much visible. 70 people who are leaving, 184 and 24. Okay. So you can see that human resource and sales, both of them are at the same position. They are kind of leaving the organization most frequently. Cool. Now moving to the other parameter, let's say education field. Stacked bar. You can pass first of all data, sorry. Education field, comma, the target class is basically at region. So you can see that people who are from human resource, technical degree and marketing, they are the most contributors comparative to life science, medical analysts. Right? So this shows that those people are kind of more aligned to lead the organization. Okay. So like this, you can go with all of these different parameters. Finally, let me take the job role and then we will leave it. You guys can basically stack bar HR data, comma, job role. Sales representative, 60% above is just see, it's the highest number. Okay. Sales representative, laboratory technician, human resource, sales executive, research scientist. These are the top contributors among rest of other contributors. Okay. So this is how you can see, you can do the analysis and figure out where your problem is lying. One of the interesting problems is sales representative. Okay, sales team people are leaving more, so that is already figured out. Okay. If you see the research part, research scientist until here, and then manufacturing director, these positions are quite experienced positions. So probably because of that, people are not leaving. So with this, you can basically understand which are the portion of your information is getting affected, like which particular columns or which are the having a direct relationship with their targets. With correlation, you can only find out the interrelation between your values, but with this views bivariate analysis, so this is known as bivariate analysis, where you are taking two variables, okay, attrition and one other variable, to compare the values. This is being noted as a bivariate analysis. Yeah. Just a minute, please. Okay. Any questions? Anybody? One important aspect is, it is not necessary that you always need to write some logic every time or create a function every time. Okay, like over here. Not always required. Okay? Not always required. Let me give another example where you can directly plug in. So plt dot okay, even you don't need to show, I mean, you don't need to create a figure size. SNS dot box plot feature data. You can take, let's say, performance rating. So we can take performance rating and performance percent salary hike. Okay, let us take these two data and compare between these two data. Performance rating and percent salary hike. Percent salary hike. Comma. I will show another example with filtering. With this simple thing, I took in two different variables. One is basically performance rating, another is percent salary hike. Okay. So what you can see that performance rating 3 and performance rating 4. Okay. So you get to see that their salary hikes for 3 is quite less, which is between, and that is quite obvious. Okay. For those who are getting a higher rating, they are getting more salary. This shows that there is some sort of hike present in the given annual financial cycles. So this is not a conflicting factor. So you can say that the performance height is increasing as well as performance rating is also increasing. So that is quite supporting over here. The data is quite supporting. So you don't need every time to write this, to kind of write a function and then call all the parameters one by one. Eventually you can write in this way as well, calling two different columns at the same time. With single interpretation, you can actually get the results. And if you want to add filter, let's say I want all this job role to fit into this performance rating. Then I can use hue. Okay, so you can see that it is all trying to fit within the same graph. So what I will do is I will increase. So plt.figure fig size is equal to 15,5 10 let's. So now you can see that fig size, this is just for adjusting the size of the given array. So this was a single box earlier, but when we added hue, it got into two. It's got splitted with the job roles. Any questions? So let me rename this as part 2. So now, I've shared the notebook with everyone. Now so this is all about your Pandas execution mostly. Okay. Now Pandas deals with mostly the data which are in rows and columns, like dealing with the real-time data sets. CSV file, I think it is not shared, right? Okay. We share this. Yeah. Let me create a new file for Numpy now. Okay. So let us see some examples from Numpy. Now, Pandas is more into kind of data engineering related stuff, okay, where you can kind of do all sort of mining and everything. Numpy is more into scientific techniques. The reason why you need to understand Numpy is like computing array, linear algebras, okay, all the mathematical modules. Numpy is very much important. And the reason why you need Numpy is with the help of Numpy, you can compute all those mathematical models. You can basically understand the need of those. Okay. And in sometime in terms of data engineering, what happens is like, let's say, this is one of the very common process, like and most of the organizations like Google, Amazon, they do it for data store optimization. So what we do, let me show you. So first of all, you have billions of images. Okay. You have billions of images. Now these images are basically stored in a compressed form. Okay. In database. Basically, we don't say database when we are storing images because database is more into a structured. When we say that we are storing the data in like images and all, we use some sort of cloud services. Okay, and I will actually go through all of those in more detail in our upcoming sessions. So either we go with the cloud-based execution, like more examples with the clouds, we'll go through that. So basically they are compressed. As of now, let us understand that these images are not like stored haphazardly here and there, okay, randomly just pulling the information, not like that. They are stored they are basically compressed, and eventually we also need to sometimes read these images, okay, in fact reading the image, okay, and using an optimization or compression mechanism to compress this image back. Okay. So this is also one of the tasks. Somewhere it is important in terms of your data engineering. So what happens? Let's say you have billions of images. You have a defined storage space where or you need to utilize your storage space in such a way so that you can confine that storage space with a limited data set, or you can try to increase that bandwidth rather than adding another server, another instance in the cloud. We try to first see how much well optimized we can do it, how much well compression you can do it, and post that we try to get those evaluations in place, like how well we have optimized, and then how much amount of data we can store. There where the role of Numpy comes into the picture. And this is one of the real-time instance which I am speaking of. Okay. Now, compression algorithms can be any such algorithms. Okay. So we will not get into those software development related stuff. Okay. Then again, we are linking data engineering with that, but it is more like we should have certain mechanism to read those images, read a very large array of information. This is one instance. The next instance is the next different data store issues are most of these APIs, basically Twitter API. Then you have Twitter, then you have the all social media. Social media handles. So all of these APIs are very, very important. to store these. Yeah, I will come to that. I'll come to this one. So API related informations, they are highly unstructured. Okay. So most of the time we spend in creating a lot of structure from that API hit information. API is hitting to the server and it is returning back with a lot of associated data sets, which may be important, may not be important, but it hit backs with a lot of extra information. Okay. Those are much not required. Okay. So in that instance, what we do is we basically go ahead and trim that particular API data set, and we try to convert in form of any metrics, okay, with all the responses or with all the handles. Okay. So primarily what we do, if I want to explain, okay. So basically what we are doing is used a different white marker. Anyway, so what we are trying to do with this API Twitter handle is, so you have multiple handles. Okay. So there is one thread which is kind of figuring all the relevant context from that handle and storing that information over here. Now, this is basically a database of all the handles, Twitter handles. Okay. Handles in the sense, basically the Twitter users. Okay. A person can have multiple Twitter users, specifically the celebrities. Okay. They have multiple different accounts with different context. Okay. Fan page, fan account, and blah, blah, blah. So many things are there. So this handle table or handle database helps us to fix, or next time if I want to kind of mine some information from those Twitter handles, then I can basically go to the fixed set of those handles or a range of handles. Let's say there are 10 million people, okay, following across the world. Their informations are stored in this. So in those cases, what we can do is while reading those handle database, or we can directly apply the SQL queries, we can do all of those. The other way is we can also take help of Numpy to read those in form of arrays. Okay, read those handle or all those information in form of arrays. So Numpy is of multiple use. Any mathematical execution that we do with Numpy, basically primarily used in data science and all of those concepts. Coming back to the first one, just to repeat once again. So let's say you have a billions of images and you want to compress those billion images into a single file or a single file. Obviously it is not possible, but there are certainly some techniques coming out in industry. Okay. One of the live example I would love to share. So probably let me clear the drawing so that we can see that example. This is one of the use case where I have worked in reducing the billions of records at a very small meta scale data. Okay, so it is one of the data engineering project only, and this is one of the research that we were doing it. How can we scale down a data in the form of a metadata? Okay, so in the meantime it loads, it takes a bit time to load, and I guess yeah, data compression and okay, so this is one of the patent where method of system of data compression and data storage optimization. So I was working on this particular patent when I was working with Wipro. Okay, objective over here is to take data and then how can we bring down that data at a different scale. So for an example, we were using linear algebra, okay, to take a particular set of data. So what we are doing is we are taking a particular chunk of data and converting that into some encoding techniques and applying whenever the data is repeating. So we are creating certain rules. Okay. So each and every data is kind of uniquely identified. So these are the real phases of data which are getting stored in binary, right? So, and then we are converting those into a matrix. Okay. So data is getting encoded, okay, into binary forms, and then it's a very large information, okay, with all zeros, ones, zeros, zeros, one, zero. So like that, it's a huge binary information that we are taking and then we are converting into database, wherein pushing into database, or what we can do is we can chunk out with our algorithm. It was basically 8 into 8 blocks, data blocks. And then we are passing through some algorithm which is known as row reduced echelon form. It's mostly the linear algebra algorithm. Okay. Now, why I'm emphasizing this, these are not required basically, but to give you a real-time experience. So row reduced echelon form. Okay, so this is the mathematical objective. It's basically the mathematical formula which helps us to reduce this 8 into 8 blocks into somewhere between 2 into 2 blocks. Now imagine that all these blocks are getting reduced at a very large scale. Okay, so what we have seen as an end result, like 1 GB can be reduced to some 1 MB based upon the redundancy of the data. If the data is very frequently redundant, then it can be reduced to some KBs as well. GB to KBs, just imagine. Okay, GBs to MBs. So that is what we have claimed. We also got a grant in this patent. I guess yes, we got a grant in this particular invention. So this is how we basically do. This is where your Numpy comes into the picture. So we are taking the information, converting into a matrix, and then converting into 8 into 8 blocks. This is also a Numpy application. This is also a Numpy application. Then row reduced echelon form. This is where also Numpy comes into the picture. Okay, maybe the algorithms that we have designed it of our own, but with the help of Numpy, we can structure all this information in form of arrays. Okay, so that is how. Now you can take anything. So any given image you can take, any given document you can take. Okay, text related data, anything that we are converting into a matrix, encoding it first, okay, and then converting into a matrix, then creating an 8 into 8 blocks, passing through row reduced echelon form, which is just nothing but the rules. We are not storing the data, we are storing the rules. That we are reducing the rows, means we are reducing this overall data. In spite of storing the data, we are just reducing the we are just storing the rules, that how we are reducing this entire data. That rules is basically nothing but we are defining it as a metadata. Okay, that is the size of a metadata. So metadata is basically nothing but data of data, right? It's information about your actual data. But we have changed the definition of metadata here. We are defining the entire data within metadata in form of rules. So that is how we can apply this kind of technique in order to reduce a very high dimensional data or very larger group of data. And for that, we need to understand Numpy. So this was one of the live example and implementation. Kind of you guys can follow this link if you want to kind of explore more. Rules over here are nothing but this is a part of the algorithm. Okay? In spite of storing, so rules is nothing but this is a part of our algorithm These rules are coming from this row reduced echelon form. So if I let me broaden this, you can see that R4 minus R3. Okay, so R4 is equal to R4 minus R3. So this is my rule. Okay, so we are storing this address. R4 is an address, R3 is an address. So this address R4 minus R3 address is one of the rule. Okay, then R3 plus R4 is another rule. R1 plus R3 is another rule. Then R3 square, and then is equal to R4 square. So like that, we are getting an identity matrix. You can see that we are getting an identity matrix from any given data. Like this was our original matrix, and we are converting that original matrix into an identity matrix. Okay, so this is bit mathematical for, so we are converting into an identity matrix here. Okay, so identity matrix, every time we take any data, we convert into an identity matrix. In the process of conversion, whatever the rules come into the picture, or whatever the conversion process we are doing it. Okay, so these are basically rule 4, rule 3, rule 1, rule 3. Okay, so we are storing these rules instances in spite of storing this entire data. Clear? So if you get some time, probably you can go through this entire documentation. The best way to open this is from US Patents and Google Patents also, where you can basically come and search for. The best way I feel is like, because here it will show all the similar data optimization patents. I can easily get it with my name. So yeah. So yeah, it got granted in 2020, like last year. So probably you guys can, if you want to go into more details with this invention, you can kind of get into this link and check. So these are more into the data optimization. How can we optimize? Now you can see that I haven't used any ML. I haven't used any big algorithm, just simple row reduced echelon form. This is one of the linear algebra algorithm I have used it, and I'm able to get a very good results, wherein from GBs to MBs, from 2 GB to some few MBs, 100 MBs. That is quite a good optimization that we are doing. And this is basically not a lossy compression. Compression is of two types. One is lossy, another compression is lossless. Lossy means you might see some graded, or the quality of transformation may not return all the variables. Okay, so if you see in WhatsApp, okay, you send an image, the image loses some of the property. So it is a lossy transformation. Okay, so WhatsApp is not taking your image actual value and sending to somebody else. They are basically taking the data and then they're losing some of its properties. Okay, means they're compressing the data. Okay, compressing your images and then sending it to somebody else, so that in that transmission time they can save some time. In fact, at the same time, they want to reach with multiple people. It is not that they are having a storage issue, because this is more with transmission of an image from your device to somebody else. Now what they want to use is the MTTR, means the mean time to transit. Okay, mean time to transit from one person to another person should be minimum as possible. So if you send an actual image which can be of 5-6 MB, and like that, if you want to send 30 images, so 30 into 5 MB, 150 MB would cost the user with a higher network bandwidth, as well as the time to transmit these 150 MB across multiple billion users who are using it will be very time taking, right? So that's why they have chosen to go with lossy transformation. where you don't need to basically go with the actual value. You can lose some of the pixel properties, okay, while you transform that, or the files are getting compressed. Yeah, I'm saying that it is not the issue with bandwidth. Why they are choosing lossy, that's what I am explaining, because of the bandwidth. So files are getting compressed because they have chosen the lossy mechanism, and they don't want to get into the bandwidth part, so that their users should not uh, get stuck with that bandwidth issues. Maybe not all the users will have a very high bandwidth, right? So they might think that the WhatsApp by itself an application is not working much. So those are some internal factors while the product design happens. We do understand that lossless is something where you don't lose any properties of the data. Okay, lossless compression. So any kind of media file, or it can be an image, it can be a video, it can be any music, sound, where you don't lose any property. The actual property remains over there. So this invention is more with lossless. Okay, we are not losing any property, and that's why we are storing every instance of our rules. Okay, we can also make this same algorithm behave like a lossy. Okay, that would reduce much more data. Okay, means much that will actually help us with more compression, but it will be a lossy. In terms of lossy, we might lose some of the important property, so we won't want to go into those losing some property from the data. So that's why we have chosen to go with lossless compressions. So yeah, so these are the things that where your NumPy can take into the picture at a more wider level. So let me quickly go to NumPy. So import NumPy as NP, and let me print np dot version. And if you have not installed NumPy, so keep install -user NumPy. So this is the way you can get it installed. Okay. So I am using 1.19.3. Again, NumPy is very subjected to different other packages as well. So why you need to know NumPy is, there are a few reasons already I mentioned. In terms of data engineering, I mentioned. In terms of data science, NumPy is very much required. Like any given array, any given information, when we try to pass through any model, predictive modeling, or any given different models, we generally create an array and then we pass those variables in form of an array and then pass it to the model. One of the important aspect is there are some ML packages like TensorFlow. Okay, they actually need NumPy array. Okay, even TensorFlow have their own array system, but they basically need a NumPy array to get it. They want the data in an array structure. Data structure should be array. You can use NumPy or you can use any other TensorFlow array as well. So it doesn't matter to them, but they want the data to get fed in an array format. First of all. Second is there are many other packages which are very much relied upon NumPy. Okay, so those packages will be using NumPy for their internal computation purpose. So any error you get in those packages, you can, if you are getting an error related to your array based issues and all, you can easily fix it out with knowing NumPy. So let me create an array. So let's say digits is equal to np.array, numpy.array, and then you basically pass 1, 2, 3, 4, 5, 6, 7, 8, 9. So this becomes a kind of a matrix for us. So digits. Okay, you can see that this represents an array. So the first value will actually refer to all the, now you can slice the arrays, okay, one by one, but the data type has converted into a form of an array. Array has multiple different dimensions as we go through. So let me speak about different dimensions. Let me create different dimensions. The first is you can eventually check array, like you can check the shape. So digit dot shape, okay, which sorry. Okay, I was missing the S, digits dot shape. 3, 3. So 3 rows, 3 columns. So this is the shape that we have it. Now what we can do is we can create, let me show you multiple dimensions. Okay. So first of all, A is equal to, this is 0 dimension. It has no dimension. Okay. NP dot array, and let's say I give any one value, 42. So this is of no dimension, 0 dimension. B is equal to np dot array, and then you pass a series of values, let's say 1, 2, 3, 4, 5, 6. Then C is equal to np dot array, and inside it 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so these are your arrays, and D is equal to np dot array. Here we are going to kind of create multi-dimensional. So 1, 2, 3, 4, 5, 6. Seven, 8, 9, 4, 3, 2. Okay, so these are your arrays, different dimensions, 0, 1, 2, 3. And let me execute this all. And now let me print A dot shape, B dot shape, C dot shape, D dot shape. So you can see the interesting factor over here is first one, A dot shape is basically null. Okay, because you cannot represent a scalar value. So this is being referred as a scalar value. So you cannot represent a scalar value with the help of you cannot give any dimension. You cannot measure a single value with any rows and columns. So the dimension is 0 here. Then the next one, 1, 2, 3, 4, 5, 6. So there are 6 values present. Okay, 6 comma. There is nothing means no column. One single row with 6 different rows are there with one column. Okay, so 6 comma, just simple. 3, 3 means 3 rows, 3 column. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 rows, okay, and 3 columns. Next one, 1, 2, 3, 4, 5, 6 into a single form, and then 7, 8, 9, 4, 3, 2 into another single matrix. So here the dimension is 2, 2, 3. Okay. So basically what you are doing over here is, first of all, there is a split of 2. So let me show you, write and show you. So 1, 2, 3, 4, 5, 6, then 7, 8, 9, 4, 3, 2. So this is one particular matrix, this is another one, and all are combined in a single one. So first of all, there are 2 matrix, so that's the value of this 2, comma, there are 2 rows for each of these, comma 2, and there are 3 columns, 1, 2, 3. So 2, comma 2, comma 3. So this is the representation of, and basically 3 dimension. Okay. So this is how you can take a matrix and you can create dimensions. So there is a, you can also print the dimensions. Let me print it. Print A dot ending, B dot ending, C dot ending, D dot ending. Shapes tells you that what are the different values. The dimension tells you 0 dimension, 1, 2, 3. Okay. So this is how you actually create the NumPy arrays. Okay, with multiple different dimensions. Any dimension, there is no limit. Basically, any dimension you can create. And there is one observation that you have to do with NumPy is dimension when you are creating, it should be matched dimension. It should not be an unmatched dimension. So somewhere if you want that I want to remove one particular value from here and I want to execute this, okay, and then if I want to calculate the shape, I'm not getting the other part. Okay. Here the dimension becomes 0, 1, 1, 3. Okay. So the dimension is not getting matched. So in fact, you are not going to get a proper result out of it. See, it is becoming a one single value. So it is not able to figure out that how many exact number of columns are there. 3, 3. 3 rows are there, that is fine. But what is the exact number of column? It is not able to figure it out. Why? Because of this unmatched dimension. So you need to match it. Otherwise, you will get an output, but that will be only with respect to one particular value. Again, if I put the value back 9 here, and then if I execute, you will get the original 3, 3, and that is all fine. So whenever you are creating the matrices, make sure that you don't miss out, or you need to match the dimension. Like if you are mapping it, you should match it, unless it might treat it as a part of a vector. Okay. So this is how you actually create the matrices, or you can take an array and you can do multiple things. Eventually you can slice an array. So let's say B of 0. So this tells me, this gives me 1, B of 0. Okay, because this is only a one-dimensional array. So I'm getting the first value. But if you go with C of 0, so C is basically two-dimensional array. So first it returns the dimension. So it is returning the dimension, which is row, entire row with 3 columns. So if this is returning a dimension value, or one row with 3 columns, 1, 2, 3, and then we are putting the 0th value out. Okay, so the value is, answer is 1. Then again 1, the answer is 2. Then 2, the answer is 3. So this is how we can slice, we can reach to each and every values of a given array. So slicing can be done at any level. You can also come into D and you can slice. You need to slice those many levels based upon the dimension. Single dimension, 1 slicing, 1 indexing, 2 dimension, 2 indexing, 3 dimension. When we go to D, I need to first select which array. I want to select first array, first matrix, then I need to select the first row, and then I am selecting the second value. That makes sense. So the value is 2. Okay. First matrix, then I'm selecting first row, then I'm selecting the second value. Every indexing starts with 0, 1, 2. So 1 is my second value. Right. So this is how you have to do the indexing if you want to access the array values. Indexing is very important. because most of the time we make mistakes with indexing. So one thing to remember while you do the indexing, first check out the dimension. As many dimension you see, for every dimension there is number of indexes increases. 3 dimension, 3 index, 2 dimension, 2 index, 1 dimension, 1 index. So like this, you can remember that how many indexing you need it to pull out 1 or 2 values or a range of values. Eventually, you can also create a range of values. Okay, 1 is to 2 or something like that. 0 is to 2, something like that. You can create it. 0 is to 2 is your actual value. So 0 is to 2 means you will get the first 2 values, 0 and 1. Okay. So like this, you can pass on the range as well. If you want to pull out some section of the data, not the entire one. So range can be a fruitful results out of it. So this is what is your Numpy. There are some more interesting factors present in Numpy. So those things will be keep on learning while we navigate through our entire course. These are some introductory part of Numpy. So Numpy part 1. Any questions, anybody? Okay. Cool. So over to you, Kunal.
Okay, so are we done with the queries?
Yeah.
Great, then I think people have not been asking